Picture a colossal cargo ship, longer than 3 football fields, battling a raging ocean storm. Waves as tall as buildings crash over the deck, the sky a swirling mass of gray and black. The ship, dwarfed by the sea's fury, climbs each wave, then plunges into the trough, vanishing in a valley of water. It seems impossible that something so massive could survive such chaos. The vessel groans and shudders, tilting dramatically, as if the next wave might be its last. Yet, this is daily reality for thousands of ships, carrying the world's goods across unpredictable oceans. Rogue waves, once thought mythical, can tower over 30 meters, but these steel giants endure. How do they stay afloat and upright against such overwhelming forces? The answer isn't magic. It's centuries of science and engineering. The survival of these ships is a testament to human ingenuity and a deep understanding of the forces at play. This is the story of balance, design, and the science that keeps ships afloat. When we see a ship tossed by giant waves, our instincts scream disaster. The ship tilts steeply, and it looks like it's about to capsize, because on land, when things tilt, they fall. But our intuition fails to grasp the ship's true scale. Modern container ships are vast, stable platforms, designed to roll with the waves, not fight them. What looks like a near disaster is often the ship doing exactly what it's built to do. Camera angles exaggerate the motion, making the scene look more chaotic than it is. The ship isn't a passive victim, it's an active system, constantly correcting itself like a determined pendulum. So, next time you see dramatic footage, remember, your brain is being tricked. The danger is real, but not as immediate as it appears. These ships are marvels of engineering, built to withstand the ocean's fury. The spectacle is less about impending doom and more about resilience. It's science in action, overcoming chaos. The secret to a ship's stability lies in 2 invisible forces, the center of gravity and the center of buoyancy. The center of gravity is where all the ship's weight balances, kept low by design. The center of buoyancy is the center of the water the ship displaces. When upright, gravity pulls down and buoyancy pushes up, perfectly aligned. When a wave tilts the ship, the underwater shape changes, shifting the center of buoyancy to the deeper side. This creates a righting lever, a force that pushes the ship back upright. The further the tilt, the stronger the correcting force up to a point. Engineers calculate this precisely, ensuring ships recover from even rough seas. The ship isn't fighting the waves, it's using physics to recover gracefully. This self-correcting action is the core of ship stability. As long as the righting lever is strong, the ship wants to return upright. It's a constant, invisible ballet of forces that keep ships afloat. How can thousands of tons of steel float when a steel bolt sinks? The answer is density. A ship isn't a solid block, it's a hollow shell filled mostly with air. Its average density is less than water, so it floats just like a metal pot in a sink. Archimedes' principle explains it. A ship floats by displacing water equal to its own weight. The vast volume of air inside provides the upward push needed to support the ship. The steel hull is strong, but it's the air inside that's the real secret. This design is the first step in making ships both float and stay stable. A ship's stability changes as it loads and unloads cargo. When lighter, the center of gravity rises, making the ship less stable. Enter ballast tanks, huge compartments that can be filled with seawater. After unloading, water is pumped in, lowering the center of gravity and restoring stability. When loaded, ballast is pumped out to compensate. Ballast tanks also help control trim, front-to-back balance, and list, side-to-side tilt. By adjusting water in specific tanks, the crew keeps the ship level and efficient. This system is dynamic. Officers monitor and adjust ballast throughout the voyage. It's a simple, ingenious use of seawater to keep ships balanced and safe. Ballast tanks are a cornerstone of modern shipping stability. Waves aren't just walls of water, they're energy moving through the sea. As a wave passes, it lifts the ship, then sets it down. The ship rides the wave, not carried away by it. Ships move in 6 ways: surge, sway, heave, roll, pitch, and yaw. Rolling is the most dangerous, so ships are engineered to handle it safely. Surprisingly, ships are designed to flex. A 400-meter vessel bends as it rides waves. This flexibility prevents structural failure from immense stresses. The hull shape, weight distribution and flexibility all help the ship move with the sea, not against it. The righting forces we discussed are always at work, bringing the ship back to stability. It's a dynamic dance, absorption and recovery, not brute resistance. This is how steel giants survive the ocean's most powerful forces. Ships are built to move with the sea, not fight it. The hull's shape is crucial for speed, efficiency, and stability. Large cargo ships have wide, flat bottoms for initial stability, like standing with feet apart. As the ship rolls, the hull's flare increases water displacement on one side, shifting buoyancy and creating a strong righting force. Bilge keels, long fins along the hull, act like shock absorbers, damping rolling motion. They don't stop rolling, but make it slower and safer. The bow is shaped to cut through water and handle waves. Many ships have a bulbous bow for efficiency and smoother rides. Every curve and angle is designed for stability and safety. The hull is a masterpiece of engineering, balancing all the forces at play. It's the foundation of a ship's ability to survive the sea. Despite all this engineering, ships do occasionally capsize, but it's rare. It's almost never just a big wave. Usually, it's a mix of extreme weather, mechanical failure, or human error. Shifting cargo can suddenly move the center of gravity, overwhelming the ship's righting ability. Engine failure in a storm can leave a ship broadside to waves, increasing the risk of capsizing. Rogue waves or synchronous rolling, where wave timing matches the ship's natural roll, can also be factors. But these are exceptions, not the rule. Modern regulations, weather forecasting, and crew training make shipping safer than ever. Every accident is studied to improve safety and design. The vast majority of cargo crosses oceans safely, proving the science works. Ship stability isn't just science, it's the backbone of our modern world. Nearly everything you use has traveled by sea. 90% of global trade moves on ships. Without stable vessels, our global economy would collapse. Every storm-weathered ship is a victory for engineering, from Archimedes to today's supercomputers. The stability of these ships is an invisible force shaping our daily lives. Next time you see a container ship, see it as a masterpiece of applied physics. Its ability to stay upright is the result of human curiosity and ingenuity. With science, we've turned treacherous oceans into highways of prosperity.